In this example, let's do a more complex energy balance problem. Given superheated steam at 40 bar, absolute pressure and 500 degrees Celsius. I like to draw the flow chart while I'm reading the problem statement. Saving some time is easier to understand, and you don't have to go back and forth. And given this is superheated steam, and based on that information, you know which table to go to in the book. And 40 bar is absolute pressure. The mass flow rate is 250 kilogram per minute and flowing to a turbine, and this turbine is adiabatic. Which means that the heat is zero, is insulated. And the turbine also develop 1500 kilowatt work. Well, because we talk about if the system is doing work to the surrounding, the work will be negative. So summary mark is as negative 1500 kilowatt. And the turbine expands to 5 bar. It doesn't say it's absolute or not, but based on the problem statement in the previous one, it's absolute pressure. And from there, turbine flow. From the turbine, the heat flow into a heater. And the heater reheat the steam isobarically. Isobaric means the same pressure. So the pressure is constant and reheat to initial temperature. Okay. Initial temperature is 500 degrees Celsius. And the same pressure, that is 5 bar. Again, we can assume that this is absolute pressure based on the problem statement for the first one. Okay, now it's asking for the outlet stream temperature on the turbine. So looking for this temperature. So first I draw the flow chart. We'll just draw the flow chart and label the variable. What else? Well, it's better for the energy problem, it's better to write down the specific enthalpy. So we can look for specific enthalpy from the table B7 in your textbook. From table B7. And looking for pressure on the first column, that's a pressure, is 40 bar. And looking for 500 degrees Celsius, and then you will get 3445, and the unit is kilojoule per kilogram. Okay, and we don't know this one because we don't know the temperature, but we can find out the specific enthalpy by energy balance, and from there we can find the temperature associated with a specific enthalpy. And the last one, well, let's just look at the turbine for now, because that's what we deal with the first problem. First problem is asking to determine the temperature on the turbine, the outlet stream. Okay, so after draw the flow chart, and obviously because there's mass flow in and flow out, so this is a perfect open system. And then we can write down assumption. What do I assume to achieve the goal? Well, I want to let my readers know I assume, based on the problem statement, there's no velocity term, so you can ignore kinetic energy. Why you really say can ignore kinetic energy, and it doesn't look like there's elevation change, so we can also ignore potential energy. And based on the problem statement, we can assume this is open system, continuous steady state. and this is on the turbine. Again, you see that on the turbine is adiabatic system, so the heat is 0. Okay, next step, let's write down the material balance for an open system. Well, again, this is an open system. For an open system, continuous steady state, material balance is input equal to output, and the input is m dot mass flow rate is 250 gram per minute. That is for both input and output. And then write down energy balance. Energy balance based on open system continuous steady state. Then we have change in enthalpy plus change in kinetic energy. Well, because it's open system, there's a flow rate, so it is dot on top of the energy term equal to heat flow and shaft work. Also, we can also write down assumption that there's no mass crossing the boundary doing work, so we can say there's no boundary work. Boundary work also referred as flow work in the book. Okay. Now, based on the assumption, we can cancel out this term, and this is 0. Therefore, we get the net energy balance equation is simply change in enthalpy equal to shaft work. Okay. Then given shaft work is negative 1500 kilowatt, then we just have to solve for change in enthalpy. For change in enthalpy, and we have specific enthalpy, and we have the mass flow rate, then we can calculate that easily. And we know that enthalpy is a state function, depends on the final state minus initial state, or we say the outlet stream minus initial stream. In this case, is the outlet stream minus initial stream for specific enthalpy. And we already know this guy, but we don't know this guy. But we know that the total of this is 1500 kilowatt. Now we can substitute the number in the equation, given that given mass flow rate is 250 gram per minute. There is an issue, is given kilogram per minute. We have to convert that to second to get kilowatt, because the watt is joule per second. Okay, so we have to convert that. So 1 minute is 60 seconds, and this guy we don't know yet, and we already found out the specific enthalpy at inlet stream is 3445, and is kilojoule per kilogram. Okay, make sure they're the same units so they can cancel out. Okay, so we have only one unknown variable. It can be solved easily. Take out your calculator, and we can solve that. We get 3085 kilojoule per kilogram. That is the specific enthalpy in the outlet stream. Then we can look at the table in B7 again. Find any specific enthalpy that close to this value. We don't see any value close to this guy, but we do find there is between 3085, we have 3168, and we also have that is associated with the temperature of 350. This is temperature degrees Celsius. This is 350, and at 300 degree is 3065. That is 300 degree. Then we can do interpolation because they are all linear relationship, and we know that on a linear curve or straight line, the slope is the same from different point interval. So let's say this is a t, and this is 300, this is 350, and again my x-axis is temperature, my y-axis is specific enthalpy, and specific enthalpy had the unit kilojoule per kilogram, and this is degrees Celsius. And associated with 300 degree is 3065. Associated with this one, I run out of space, I'm just gonna write down here. So we know the slope are the same. This is the slope. Then we can do interpolation from 350 to this one. Well, because we have calculated that this is 3085. Okay, so from temperature 350 to the unknown temperature, and 350 to 300 degree, the slope is the same. So based on that information, we can write down, well, because the slope is change in y over change in x, or you can write dy over dx in derivative term. So this associated with 300 degree, this is the T2 associated with the temperature that we are looking for, and this associated with 350 degree. Okay, now minus T, 350 minus 300, this is 300. Well, you can write in the denominator, it doesn't matter, because I like to put them all together. Just make sure they're the same, because the slope is change in y over change in x. So you can have y1, or you can write y minus y1, or y2, and y2 minus y is x2 minus x1 over x2 minus x, and you can move back and forth, right? Now, based on this information, let me clear this. It looks too messy. Okay, there you go, better. Alright, so we only have one unknown variable, then we can solve that easily. Then we simply get T2 is close to 110 degrees Celsius. That is the answer for A.